Hi, this is David Quatello at Siemens, and welcome to the Basics of Controls for Construction. This course covers basic control concepts as applied to construction market applications and provides an overview of Siemens control products that are appropriate for the construction market. You should have a basic understanding of electrical concepts to fully benefit from this course. Let's get started. And here we're just showing the required trademarks. Upon completion of this course, you will be able to state the purpose and general principles of control components and circuits, state the difference between manual and automatic control operation, identify various symbols which represent control components, read a basic line diagram, describe the construction and operating principles of manual starters, electromagnetic contactors, and electromagnetic motor starters, explain the need for motor overload protection, briefly describe the operation of thermal and electronic overload relays, summarize the types of NEMA control products offered by Siemens, describe the advantages of reduced voltage motor starting, describe the type and operating principles of lighting contactors, identify the types of pilot devices offered by Siemens, and finally describe the function and basic characteristics of a control power transformer. So here's today's agenda and course topics. This course has 4 parts, plus a final exam. The first part is an introduction that covers control concepts. The second part covers basic motor starter concepts. The third part covers Siemens motor starters. And the fourth part covers other Siemens control components. After each section, we'll have a 5 questions knowledge check, and then at the end of the course itself, there will be a final exam. Control, as it relates to machines and processes, is a broad term that means anything from a simple toggle switch to a complex system. Control is considered to be manually operated when someone must initiate an action for the circuit to operate. For example, someone might have to flip the switch of a manual starter to start or stop a motor. Although manual operation of machines is still common, many machines are controlled automatically. Frequently, there is a combination of manual and automatic control. For example, a machine that is started manually may stop automatically when certain conditions are met. While many control components are used in circuits that involve motors, control components are also used with a variety of other equipment. Various types of control components are used for switching, starting, protecting, detecting, monitoring, communicating, and other functions. The full range of these capabilities is beyond the scope of this course, but examples of devices that perform these types of functions are discussed throughout the course. Before discussing specific control devices, however, it's important to understand some basic symbols and diagrams. The symbols and diagrams described in this course are commonly used in North America. Other types of symbols and diagrams are also used. Contacts are part of a control device, such as a control relay or contactor. Contact symbols are used in a control diagram to indicate an open or closed path for current flow. Contacts are shown on the control diagram in the state that exists when the control device is de-energized. This is referred to as the normal state of the contacts. Therefore, contacts are shown as normally open, NO, or normally closed, NC. For the purpose of illustration in this course, a contact or device shown in the opposite of its normal state is highlighted. In the lower left corner of the accompanying graphic, normally open relay contacts are shown. When the relay is de-energized, the contacts are open, but when the relay is energized, the contacts are closed. When the contacts close, current from the battery flows through the lamp. In the lower right corner of the accompanying graphic, normally closed relay contacts are shown. When the relay is de-energized, the contacts are closed, allowing current to flow through the lamp. When the relay is energized, the contacts open and the lamp turns off. We also use symbols to show switches and to indicate under which conditions the switch provides a path for current flow. There are many types of switches, such as limit switches, foot switches, pressure switches, level switches, temperature activated switches, flow switches, and selector switches. Each switch type has its own symbol. Switches require another device or action to change their state. In the case of manual switches, someone must manually change the switch position to change the state of the switch. For example, there are 2 general types of push buttons, momentary and maintained. The contacts of a momentary push button change state. open to closed or vice versa when the push button is pressed. They return to their normal state as soon as the button is released. In contrast, a maintained push button latches in place when pressed. It must be unlatched to allow it to return to its normal state. The accompanying graphic shows examples of two simple circuits, one with a normally open momentary push button and the other with a normally closed momentary push button. Note the condition of the lamp when each push button is in its normal state. Motor starters, contactors, and relays are examples of devices that open and close contacts electromagnetically. The electromagnet in these devices is called a coil. A coil is commonly symbolized as a circle with one or more letters and possibly a number inside. The letters often represent the type of device, such as an M for motor starter or CR for control relay. A number is often added to the letter to differentiate one device from another. The contacts controlled by a coil are labeled with the same letter and number as the coil so that it is easy to tell which contacts are controlled by each coil. A coil often controls multiple contacts, and a combination of normally open and normally closed contacts may be used. In the accompanying example, the M contacts in the power circuit for the motor are controlled by the M contactor coil. Closing the switch completes the current path through the coil. The M contactor coil actuates the M contacts, providing power to the motor. There are many other types of control symbols, too many to include in this course, but some examples of symbols you will encounter later in this course are shown in the accompanying graphic and described below. Overload relays are used to protect motors from overheating. When excessive current is drawn for a predetermined amount of time, the overload relay's contacts open, removing power from the motor. The accompanying symbol is for contacts associated with a thermal overload relay. An overload relay used with a three-phase motor has three such contacts, one for each phase. An indicator light, often referred to as a pilot light, is a small electric light used to indicate a specific condition of a circuit. For example, a red light might be used to indicate that a motor is running. A letter in the center of the indicator light symbol is sometimes used to indicate the color of the light. Control circuits are depicted with line diagrams, also called ladder diagrams. Line diagrams show the functional relationship of components and devices in a circuit, not the physical relationship. In the accompanying graphic, the upper illustration shows the physical and electrical relationship between a push button and a pilot light. In the lower illustration, the line diagram symbolically displays the functional relationship of these same components. In order to properly interpret this diagram, you must read it from left to right, starting at L1 and ending at L2. With that in mind, note that pressing the push button allows current to flow from L1 to L2 through the push button and the pilot light. Because the push button used is a normally open push button, the pilot is on only when the push button is pressed. Releasing the push button stops current flow, and then the light turns off. Line diagrams are made of two types of circuits, control circuits and power circuits. Within a line diagram, control circuit wiring is represented by a light line, and power circuit wiring is represented by a heavy line. A small dot or node at the intersection of two or more wires indicates an electrical connection. The accompanying line diagram includes both power and control circuits. The power circuit, drawn with a heavy line, is a circuit that supplies power to the motor. The control circuit, drawn with a light line, controls the distribution of power to the motor. A typical control circuit includes a control load and one or more components that determine when the control load will be energized. Some control loads, such as relays and contactors, activate other devices, but other control loads, such as indicator lights, do not. For example, in the accompanying graphic, Circuit 1 shows the connection of a pilot light and the push button. The power lines are drawn vertically and marked L1 and L2. In this example, the voltage between L1 and L2 is 120 volts. This means that the pilot light must be rated for 120 volts because when the push button is pressed, 120 volt is applied to the light. While it is proper to place contacts in series, it is not proper to place control loads in series as shown in Circuit 2. In this circuit, when the push button is pressed, the voltage is divided across both loads with neither load receiving the full 120 necessary for proper operation. Circuit 3 shows an example of a correctly connected circuit with a few more components. In this circuit, a normally open push button is connected in series with two parallel branches. One parallel branch has a pilot light and the other has a contactor coil in series with set of normally closed overload contacts, OL. This configuration is proper because closed contacts have minimal voltage drop, so the full control voltage is applied to both the pilot light and contact coil when the push button is pressed. Often, a load is controlled by more than one device. These control devices may be connected in series, parallel, or in combination series parallel circuit. For example, in circuit 1, two normally open push buttons are connected in parallel. Pressing either push button or both push buttons allows current to flow from L1 through the indicator light to L2. In circuit 2, normally open push buttons are connected in series. Both push buttons must be pressed at the same time to allow current to flow from L1 through the load to L2. In circuit 3, normally open push buttons 1 and 2 form parallel branches in series with normally closed push button 3. If either push button 1 or 2 or both are pressed, current flows from L1 through the load to L2 unless push button 3 is pressed. When push button 3 is pressed, no current can flow from L1 to L2 regardless of the states of push buttons 1 and 2. For these examples, the control devices are all push buttons. Keep in mind that other types of control devices or contacts are often used and the circuits can get much more complex. Some of the control components covered in this course are designed to protect motors or other equipment. In order to understand these control components, you must have an understanding of some common circuit faults. To begin with, current flows always generate heat. The amount of heat generated is proportional to both the amount of current flow and the resistance of the conductive path. Because conductors can be damaged by excess heat, each conductor has a continuous current rating, also called its ampacity. Excessive current is referred to as overcurrent. An overcurrent may result from a short circuit, overload, or ground fault. The first two types of overcurrent faults are described in the following pages. A short circuit occurs when two bare conductors touch, causing the resistance between the conductors at that point to drop significantly. This reduction in resistance causes current to rise quickly. For example, if the voltage between the conductors is 240 volts and the resistance of the conductors from one side of the power source to the other is 24 ohms, the current in the conductors is 10 amps. With the insulator intact, no current flows through the insulator from one conductor to the other. However, if the insulator between the conductors is damaged and the bare conductors touch, the resistance between the conductors drops and the current rises rapidly. For example, if the resistance between the bare conductors drops to 0.024 ohms and the voltage applied is 240 volts, the current will be 10,000 amps. For this reason, the conductors must be protected by a circuit breaker or fuse to stop the flow of current before it reaches this dangerous level. An overload is typically a much lower current than a short circuit. An overload occurs when too many devices are connected to a circuit or when electrical equipment is made to work beyond its rated capabilities. For example, if a conveyor jams, its motor may draw 2 or more times its rated current. In the previous example, the overload resulted when a circuit exceeded its rated capacity for an extended time. In such a situation, an overcurrent protection device should shut down the circuit. A different response is required for a short duration overload. In such a situation, it may be undesirable to disable the circuit. To understand this better, consider what happens when an electric motor is started. When most motors start, they draw current in excess of their full load current rating. For example, a NEMA design B motor typically has a starting current that is about 6 times its full load current. For some high efficiency motors, the starting current is even higher. Motors are designed to tolerate a high starting current for a short time. As a motor accelerates to operating speed, its current drops off quickly. In the accompanying example, the motor's starting current is 600% of its full load current, but after 8 seconds, current has dropped to the rated value. Fuses and circuit breakers are designed to protect circuit conductors in the event of a short circuit or overload. Under such conditions, these devices open the path for current flow before damage to conductors occurs. In a motor circuit, conductors and the fuse or circuit breakers are designed to protect them must be sized to allow for the high starting current of the motor. Because of this, overload protection for the motor must be provided separately. That concludes section 1, so let's start in with our first knowledge check. Question 1. In a line diagram, symbols are usually shown in the blank state. Is it A, energized, or B, de-energized? Question 2. Line diagrams are read from blank and blank. Is it A, right to left, top to bottom, B, left to right, top to bottom, C, left to right, bottom to top, or D, right to left, bottom to top? Question 3. Blank contacts are open when the control device is energized. Is it A, normally closed, or B, normally open? Question 4. A blank is commonly symbolized in a line diagram as a circle with one or more letters and possibly a number inside. Is it A, normally closed contact, B, normally open contact, or C, a coil? Question 5. A/An blank occurs when too many devices are connected to a circuit or when electrical equipment is made to work beyond its rated capabilities. Is it A, a ground fault, B, an overload, or C, short circuit? This section of Basics of Controls for Construction covers basic motor starter concepts. As the name implies, manual controls are devices that are operated by hand. A simple knife switch, like the one shown here, was the first manual control device used to start and stop motors. The knife switch was eventually replaced by manual and magnetic starters. A manual starter consists of a manual contactor, such as a simple switch mechanism and an overload protection device. Each set of contacts engaged by the manual starter is referred to as a pole. The accompanying graphic shows a single starter pole for simplicity, but manual starters typically have 2 or 3 poles. A starter is connected between the power source and the motor. This example shows the connections for a 2-pole starter used for a single-phase AC motor. A similar arrangement would be used for a DC motor. When the switch is in the off position, the switch contacts are open and current cannot flow through the motor. When the switch is in the on position, the switch contacts are closed, current flows through the motor, and the motor runs, unless an overload condition causes the overload contacts to open. Siemens SMF fractional horsepower starters provide overload protection and manual on-off control for small motors. SMF starters are available in 1-pole or 2-pole versions suitable for AC motors up to 1 horsepower and 277 volts. The 2-pole version is suitable for DC motors up to 3/4 horsepower and 230 volts DC. A melting alloy type overload relay is used for overload protection. SMF manual starters are available in a variety of enclosures. A 2-speed version is also available. Siemens MMS and MRS manual switches are similar to SMF starters, but do not provide overload protection. MMS and MRS switches only provide manual on-off control of DC and single-phase or 3-phase AC motors where overload protection is provided separately. These devices are suitable for use with 3-phase motors up to 10 horsepower and 600 volts AC and up to 1.5 horsepower and 230 volts DC. MMS and MRS manual switches are available in various enclosures. 2-speed and reversing versions are also available. Siemens Class 11 across-the-line manual starters and switches provide control for machinery where motor start and stop control is not required. Class 11 3RV manual starters are used for single-phase and 3-phase motors up to 20 horsepower at 575 volts and have bimetallic heater elements that provide Class 10 overload protection. These starters have ambient temperature compensation. A built-in differential trip bar reduces tripping time in the event of a phase loss condition. Class 11 3RV switches provide control where overload protection is not required or is provided separately. Class 11 3RV controllers are available with low voltage protection, which automatically opens the power poles when the voltage drops or power is interrupted. They are available in an open style without enclosure, in a NEMA 1 general purpose enclosure, and in NEMA 7 and 9 or NEMA 3 and 4 NEMA 7 and 9 enclosures for hazardous locations. Most motor applications require the use of remote control devices to start and stop the motor. Magnetic contactors similar to the one shown here are commonly used to provide this function. Like many other control components, contactors are most often manufactured to specifications provided by either the National Electrical Manufacturers Association, NEMA, or the International Electrotechnical Commission, the IEC. Because construction applications typically use NEMA controlled products, except where noted, this course emphasizes these products. As discussed later in the course, some magnetic contactors are used to control the distribution of power in lighting and heating circuits. Magnetic contactors utilize basic electromagnetic principles. To understand these principles, consider a simple electromagnet fashioned by winding a wire around a soft iron core and connecting the coil to a DC voltage source. Current flowing through the wire temporarily magnetizes the iron core coil. When the coil is disconnected from the DC voltage, the current stops and the iron core coil returns to its non-magnetic state. The accompanying graphic shows the interior of a basic contactor. There are two circuits involved with the operation of a contactor: the control circuit and the power circuit. The control circuit is connected to the coil of an electromagnet, and the power circuit is connected to the stationary contacts. The operation of this electromagnet is simple to the operation of the electromagnet made by wrapping a wire around a soft iron core. When the control circuit supplies power to the coil, a magnetic field is produced, magnetizing the electromagnet. The magnetic field attracts the armature to the magnet, which, in turn, closes the contacts. With the contacts closed, current flows through the power circuit from the line to the load. When current no longer flows through the control circuit, the electromagnet's coil de-energizes. The magnetic field collapses, and the movable contacts open under spring pressure. The accompanying graphic symbolically shows the operation of a contactor in simple three-phase motor circuit. The contacts of the contactor are in the power circuit for the motor. The OL contacts are part of an overload relay used to protect the motor. Overload relays are discussed later in the course. The electromagnetic coil of the contactor is connected through a switch, the SW1, to L1. Normally, other components are used instead of a toggle switch, but the principle remains the same. When SW1 closes, the contactor's coil energizes, closing the M contacts and applying power to the motor. Opening SW1 de-energizes the coil, opening the M contacts and removing power from the motor. Contactors are used to control power in a variety of applications. When used in motor control applications, contactors can only start and stop the motors. Contactors cannot sense when the motor is being overloaded, and they provide no overload protection. Most motor applications require overload protection. Although some small motors have overload protection built into the motor, more commonly, overload relays, such as the one shown in the accompanying graphic, are used. Overload relays are designed to meet the special protective needs of motors. Overload relays continue to provide power during the short duration overloads that occur when a motor starts. If an overload condition persists, however, the overload relay removes power from the motor. Once the overload condition has been corrected, the overload relay can be reset to allow the motor to be restarted. An overload relay has a trip class rating which identifies the maximum time, in seconds, it takes for the overload relay to trip at a specific current, typically 6 times its continuous current rating. The most common trip classes are 5, 10, 20, and 30. The accompanying graphic symbolically shows a motor circuit with contactor contacts, M, and overload relay contacts, OL. The circuit on the left shows the contactor and overload relay contacts closed and the motor is running. The circuit on the right, an overload has occurred and the overload relay contacts have opened. The normally closed overload relay contacts in the control circuit also opened when the overload relay tripped. This interrupted current flow in the contactor coil, causing the contactor contacts to open. In this circuit, if the overload relay is reset with SW1 switch closed, the motor will automatically restart. For this reason, most motor control circuits are configured differently, as will be described later in the course. A thermal overload relay, also called a bimetal overload relay, incorporates a small heater element wired in series with the motor and a bimetallic strip. For simplicity, the accompanying graphic shows only one circuit phase. The bimetallic strip functions as a trip lever. It is made of two dissimilar metals bonded together. These metals have different thermal expansion characteristics, causing the bimetallic strip to bend when heated. Under normal operating conditions, the heat generated by the heater element causes the bimetallic strip to bend only slightly, not enough to trip the overload relay. If an overload occurs and persists long enough, the bimetallic strip bends until the overload relay is tripped. This causes the overload relay's contacts to open, removing power from the motor. Some thermal overload relays are designed to reset automatically after the bimetallic strip is cooled. Depending on the circuit, the motor may then restart automatically. For some applications, this is desirable, but for most applications, it's not. In some applications, submersible pumps for example, the motor is installed in a location with a constant ambient temperature while the overload relay is installed in a location with a varying ambient temperature. Because the bimetallic strip in an overload relay bends more as ambient temperature rises, this can lead to nuisance tripping if a standard thermal overload relay is used. Ambient compensated thermal overload relays overcome this problem by using a compensated bimetallic strip along with a primary bimetallic strip. In the accompanying graphic, the circuit on the left shows how. As the ambient temperature rises, both bimetallic strips bend equally and the overload relay does not trip. For simplicity, the accompanying graphic shows only one circuit phase. In the circuit on the right, in the accompanying graphic, current flows through the motor and the heater element affects only the primary bimetallic strip. When the current rises to the level of an overload, the primary bimetallic bends enough to trip the overload relay. Siemens Class 48 ambient compensated thermal overload relays are available in single-phase and three-phase designs and can be set for manual or self-resetting operation. An adjustment dial located on the unit allows the ampere trip setting to be adjusted plus or minus 15%. A manual test button is provided to test the operation of the overload relay control contacts. The ambient compensated thermal overload relay heater elements are available in Class 10 or 20 ratings. A normally open or normally closed auxiliary contact is available as an option. Electronic overload relays are another option for motor protection. The features of electronic overload relays vary, but there are a few common advantages. One advantage of the electronic overload relay is that they do not require heaters. This eliminates the need to stock multiple heaters to match motor ratings. This heaterless design also allows electronic relays to be insensitive to the ambient temperature, which minimizes nuisance tripping. In addition, electronic overload relays can detect a power phase loss and quickly disconnect the motor from the power source. This is an important advantage because without phase loss protection, loss of a power phase can quickly result in damaged motor windings. Like other electronic overload relays, ESP200 electronic overload relays eliminate the need for heaters. Instead of installing a heater, a dial on the overload relay is set to the motor's full load current rating. Class 48 ESP200 electronic overload relays, like the one shown in the accompanying graphic, have two dual inline package DIP switches accessible from the front that simplify selection of any of four trip classes, 5, 10, 20, and 30. Additional DIP switches provide on or off settings for phase unbalance, phase loss, or ground fault detection, as well as selection of manual or automatic reset. Also accessible from the front is the reset button, for use when manual reset is selected, and the test button that triggers a complete electronic functions test. One normally open auxiliary contact and one normally closed auxiliary contact are standard. In addition to Class 48 ESP200, two other types of ESP200 electronic overload relays are available. The 958 ESP200 electronic overload relays are specifically designed for sealed compressors and artificially cooled motors. The 958L electronic overload relays are specifically designed for the oil market and pumping applications with a precise trip curve. We just finished section 2, so now it's time for another knowledge check. Question 1. Which of these Siemens manual control products provides overload protection? Is it A, MMS manual switches, B, MRS manual switches, C, SMF manual switches, or D, all of the above? Question 2. Both the National Electrical Manufacturers Association, NEMA, and the International Electrotechnical Commission, the IEC, provide specifications for control components, but for construction applications, NEMA control products are more common. Is it A, true, or B, false? Question 3. The blank circuit for a contactor determines when the contactor's coil will be energized. Is it A, power, or B, control? Question 4. An overload relay has A/N blank that identifies the maximum time in seconds it takes for the overload relay to trip at a specific current. Is it A, ampere rating, B, voltage rating, or C, trip class? Question 5. Siemens ESP200 electronic overload relays have DIP switch settings on the front of the relay to select, is it A, trip class, B, phase unbalance detection, C, phase loss detection, D, ground fault detection, E, manual or auto reset, or is it F, all of the above? Now we're on to section 3. This part of Basics of Controls for Construction covers Siemens motor starters. Contactors and overload relays are separate control devices. When a contactor is combined with an overload relay, it's called a motor starter. Motor starters manufactured to NEMA specifications are referred to as NEMA starters. Siemens manufactures a full line of open and enclosed NEMA starters. When a starter's contactor is set up to supply the full line voltage to a motor, it is called a full voltage across the line or direct motor starter. As discussed later in this course, some starters are capable of reversing motor direction, controlling the starting voltage, or controlling two-speed motors. However, the most common type of motor starter is designed to turn a motor on and off and provide overload protection. The overload relay used may be a thermal overload relay or, as in the accompanying graphic, an electronic overload relay. The accompanying graphic shows the electrical relationship between the contactor and overload relay in a full voltage motor starter circuit. The contactor, highlighted in light blue, includes the electromagnetic coil, the main motor contacts, and the auxiliary contact. The overload relay, highlighted in light green, includes the overload relay heaters and the overload relay contact. In this circuit, no power flows in either the power or control circuits when the electromagnetic coil is de-energized. When the start push button is pressed, current flows through the electromagnetic coil, which is labeled as M, and the associated contacts close. This causes current to flow to the motor. Even after the start push button is released, the electromagnetic coil will remain energized because the normally open auxiliary contact, MA, closed when the coil first energized. Current will continue to flow to the motor unless the stop button is pressed or an overload causes the overload relay contacts to open. NEMA-rated contactors and starters have size numbers from size 00 to size 9 based upon their continuous current and horsepower ratings. Siemens also has what are called half sizes available for some Siemens motor starters. The ratings for these devices fall between the ratings of normal NEMA sizes, allowing the user to more closely match the motor control to the actual application. Half sizes are beneficial because they cost less than larger NEMA size starters. The accompanying table shows both the NEMA sizes and the Siemens half sizes available. NEMA motor starters and contactors can be used in virtually any application at their stated rating, from simple on-off applications to more demanding applications that include plugging and jogging. To select a NEMA motor starter for a particular motor, one needs only to know the horsepower and voltage of the motor. However, if there is considerable plugging and jogging duty involved, Even a NEMA-rated device may require D rating. Class 14 NEMA starters with ambient compensated thermal overload relays are available up to 100 horsepower at 460 VAC, and these are NEMA sizes 00 through 4. In addition to whole sizes, this range includes 1 3/4, 2.5, and 3.5 sizes. These starters are available with Class 10 or 20 ambient compensated thermal overload relays. Class 14 ESP200 starters use the same contactors as Class 14 NEMA starters equipped with thermal overload relays for NEMA sizes 00 through 4, but are supplied with an ESP200 electronic overload relay. In addition, these starters are available with contactors up to and including NEMA size 8. The ESP200 overload relay provides users with the specific level of protection they desire. For example, the trip class 5, 10, 20, or 30 is set up using DIP switches on the front of the unit, and the full load ampere FLA dial allows for the wide range 4-to-1 of adjustment. As previously mentioned, 958 and 958L ESP200 solid-state overload relays are also available for specified applications. Many applications require a motor to run in either direction. Changing the direction of rotation requires changing the direction of current flow in the motor windings. For a three-phase induction motor, this is done by reversing two of the motor leads, typically T1 and T3. The accompanying graphic shows a three-phase reversing motor circuit with two sets of contacts. The forward, F, contacts are controlled by the forward contactor, and the reverse, R, contacts are controlled by the reverse contactor. When the F contacts are closed, current flow through the motor causes it to turn in a clockwise direction. When the R contacts are closed, T1 is connected to L3 and T3 is connected to L1, causing the motor to rotate in a counterclockwise direction. Mechanical interlocks prevent both forward and reverse circuits from being energized at the same time. Siemens offers Class 22 reversing starters and Class 43 reversing contactors in NEMA sizes 00 through 8, including Siemens half sizes. Class 25 and 26 combination reversing starters are available as well. The synchronous speed of a three-phase induction motor is a function of the supply frequency and the number of poles. This speed is the rate in RPMs for the motor's rotating magnetic field. The actual speed of the motor is the synchronous speed minus slip caused by the motor's load. Two types of induction motors that provide for two-speed control using magnetic starters are separate winding motors and consequent pole motors. Consequent pole motors with two speeds on a single winding require a starter which reconnects the motor leads to half the number of effective motor poles for high-speed operation. For this type of motor, the low speed is 1/2 the high speed. Separate winding motors have a winding for each speed and provide more varied speed combinations because the low speed need not be 1/2 the high speed. Starters for separate winding motors consist of a starter unit for each speed. Siemens offers Class 30 two-speed heavy-duty starters for separate winding and consequent pole motors used in constant torque, variable torque, and constant horsepower applications. Starters are available in NEMA sizes 0 through 4, including Siemens half sizes. Overload protection is furnished either with an ESP200 electronic overload relays or ambient compensated thermal overload relays. Siemens also offers Class 32 combination two-speed heavy-duty starters. Combination starters incorporate a motor starter, short circuit protection, and a means to safely disconnect power. Siemens offers a variety of enclosed combination starters and non-combination starters with NEMA components and a full range of enclosure types. Duplex motor controllers consist of two motor starters in a common enclosure. Siemens duplex motor controllers are specifically designed for applications that require duplex controls, such as for dual pumps or blowers. Siemens Class 83 is a non-combination duplex motor controller. Siemens Class 84 is a combination duplex motor controller with two separate disconnects or circuit breakers. The motor starters discussed thus far have all been full voltage starters. This is the most common type of motor starter because the initial component cost is low. A full voltage starter is also referred to as an across-the-line starter because it starts the motor by applying the full line voltage. When a motor is started with full voltage, starting current can be as high as 6 times the full load current for standard 3-phase induction motors and as high as 12 times the full load current for high efficiency motors. This high starting current causes power fluctuations that affect other equipment. As a result, many power companies require reduced voltage starting for large horsepower motors. Another potential problem with full voltage starting is the high torque developed when power is first applied to the motor. As shown in the accompanying speed torque curve for a NEMA B motor, the starting torque, also called locked rotor torque, is typically around 150% of full load torque. Additionally, the torque can rise as high as 175 to 200% of full load torque as the motor accelerates to rated speed. Many applications require the starting torque to be applied gradually. For example, a belt-type conveyor application often requires the starting torque to be applied gradually to prevent belt slipping and bunching. Also, in any application that involves frequent starts, the higher initial starting torque over time results in higher maintenance costs due to repeated mechanical shock. Starting methods which start a motor with less than full voltage are referred to reduced voltage starting. These approaches also reduce starting torque. Siemens offers the following types of reduced voltage starters with NEMA components: auto transformer starters, part winding starters, and Y delta starters. One of the more basic types of reduced voltage starters is the auto transformer reduced voltage starter. Auto transformer reduced voltage starters provide a high starting torque per ampere of line current and are typically used for applications where starting current must be reduced while retaining good starting torque. Auto transformers have adjustable taps to set the reduced starting voltage as a percentage of the full line voltage. Siemens offers auto transformer starters as Class 36 non-combination starters and Class 37 combination starters with a fusible or non-fusible disconnect or circuit breaker. Part winding reduced voltage starters are used with motors which have 2 separate parallel windings on the starter. One magnetic starter engages the first set of windings when the motor is started. These windings draw about 65 to 85% of the rated locked rotor current. After a set time, a second magnetic starter energizes and places the second set of windings in parallel with the first. Part winding reduced voltage starters are the least expensive type of reduced voltage starters and use a simplified control circuit. However, they require a special motor design, are not suitable for high inertia loads, and do not have adjustments for current or torque. Siemens offers part winding starters as Class 36 non-combination starters and Class 37 combination starters with a fusible or non-fusible disconnect or circuit breaker. Y-delta reduced voltage starters are applicable only for motors with stator windings not connected internally and all 6 motor leads available for external connections. Connected to a Y configuration, the motor starts with a significantly lower inrush current than if the motor windings had been connected in a delta configuration. After a set time, starter contacts change state to connect the stator windings in a delta configuration. This increases the voltage applied across each stator winding. This type of starter is a good choice for applications that require frequent starts, low starting torque, or long accelerating times. Siemens offers Y-delta starters as Class 36 non-combination starters and Class 37 combination starters with a fusible or non-fusible disconnect or circuit breaker. Pump controllers monitor flow and/or level variables and control a pump to maintain desired values. Pump control can involve simply turning a pump on or off, or can include more advanced controls for pump speed, output pressure, etc. Siemens pump control panels are factory wired to simplify installation, provide flexible control, and protect against short circuits and overloads. Ample space is provided for field modifications and installation of accessories. Siemens offers Class 87 full voltage and vacuum starters, as well as Class 88 auto transformer starters, part winding starters, and Y-delta starters. Solid-state reduced voltage starters, often called soft starters, limit motor starting current and torque by ramping up the voltage applied to the motor during the selectable starting time. Soft starters accomplish this by gradually increasing the portion of the power supply cycle applied to the motor windings, a process sometimes referred to as phase control. Once the startup has completed, Siemens series soft starters use integrated bypass contacts to bypass power switching devices, thyristors. This improves efficiency, minimizes heat, and reduces stress on these switching devices. Some soft starters, such as the Sirius 3RW40 and 3RW44, also allow the phase control process to be applied in reverse when the motor is being stopped. This controlled starting and stopping significantly reduces stress on connected devices and minimizes line voltage fluctuations. The Sirius modular system includes Sirius 3RW30 and 3RW40 soft starters for standard applications and Sirius 3RW44 soft starters for high-feature applications. Sirius 3RW30 soft starters have an especially compact design that saves space and easily integrates with other Sirius components. 3RW30 soft starters are available for supply voltages up to 480 volts and operating current up to 106 amps at 40 degrees Celsius. Potentiometers on the front of the unit provide settings for ramp-up time and starting voltage. Sirius 3RW40 soft starters have all the advantages of 3RW30 soft starters, but have more features and are available for operating current up to 432 amps at 40 degrees Celsius. 3RW40 soft starter features include selectable motor overload protection, class 10, 15, and 20, manual or remote reset, and optional thermistor and motor protection. 3RW40 soft starters are also equipped with integrated intrinsic device protection to prevent thermal overloading of the power switching devices, the thyristors. Potentiometers on the front of the unit provide settings for the current limit, starting voltage, and ramp up and ramp down times. Sirius 3RW44 soft starters make soft starting and stopping attractive for demanding applications and combine a high degree of functionality and extensive diagnostics. 3RW44 soft starters are available for operating current up to 1214 amps at 40 degrees Celsius. A backlit display with 4-key operation simplifies the process of changing parameters. An RS-232 serial interface is provided to communicate with the soft starter ES software for easy configuration or a display for external operation and monitoring. Additional features include, but are not limited to, motor overload protection, thermistor motor protection, selectable current limiting, multiple starting and stopping braking modes, intrinsic device protection for thyristors, and optional Profibus DP communication. Siemens 3RW40 and 3RW44 soft starters are available in standalone enclosed controlled designs for smooth starting and stopping of standard NEMA design B 3-phase induction motors. These pre-engineered designs offer convenience and flexibility in a UL/CSA certified offering. Enclosed styles are available in combination and non-combination configurations through 600 horsepower and system voltages of 200 VAC, 230 VAC, 480 VAC, and 600 VAC. Class 73 includes either the 3RW40 or 3RW44 in non-combination style offerings. These non-combination styles come standard with a choice of NEMA 1, 3R, 4, or 12 enclosure, a control transformer, soft starter with built-in overload and bypass, line side power terminal block, and a reset push button. A wide variety of factory-installed options are also available. Class 74 includes all of the features of Class 73, but in a combination style design. Standard options are either a circuit breaker or fusible disconnect, providing short circuit protection and soft starting in one package. Now that we finished this section, let's go ahead and do a knowledge check. Question 1. When a contactor is combined with an overload relay, it's called a blank. Is it A, circuit breaker, B, lighting contactor, or C, motor starter? Question 2. Siemens Class 14 NEMA starters are available with either an ambient compensated thermal overload relay or an ESP200 electronic overload relay. Is it A, true, or B, false? Question 3. Siemens NEMA contactors and starters are available in NEMA sizes from 00 to blank. Is it A, 6, B7, C8, or D9? Question 4. A basic combination starter incorporates blank. Is it A, a motor starter, B, short circuit protection, C, a disconnecting means, or is it D, all of the above? Question 5. Solid-state reduced voltage starters, often called blank starters, limit motor starting current and torque by ramping up the voltage applied to the motor during the selectable starting time. Is it A, autotransformer, B, part winding, C, soft, or D, Y delta? We're now into section 4, and this part of Basics of Controls for Construction covers other Siemens control components. Many commercial lighting and heating applications require use of contactors to control the loads. One type of contactor used in these applications is an electrically held contactor, which is similar to the contactor used with a magnetic motor starter. Unlike a starter contactor, however, a lighting contactor is designed for lighting and resistive heating loads rather than motor loads. Electrically held lighting contactors have the same operating principles as the magnetic contactors covered earlier in the course. Therefore, the control circuit for an electrically held lighting contactor, as shown in the accompanying graphic, can be similar to the start-stop circuit for a motor starter. Because the contacts for this type of contactor open when control power is lost, electrically held contactors are used in applications where automatic restart after a power failure is not required or is undesirable. Also, because electrically held contactors hum when current is supplied to the coil to hold the contacts closed, this type of contactor is not recommended where the humming will disturb building occupants. Siemens Class LE electrically held lighting contactors are an economical offering with a compact, lightweight design. They are rated for tungsten lighting, incandescent filament, and ballast lighting, fluorescent HID, metal halide, mercury vapor, quartz halogen, and sodium lamp, as well as for resistive and general use loads. Siemens Class LC lighting contactors can be ordered as either electrically held or mechanically held and can be converted from electrically held to mechanically held. Mechanically held contactors, as the name implies, have contacts that once closed remain closed until opened by the contactor, even if a power outage occurs. This means that the associated load will be automatically restarted when power resumes following an outage. This also means that the contactor only receives momentary current to open or close its contacts. Therefore, less energy is used and contactor hum is eliminated. Siemens Class LC contactors are rated for tungsten lighting, incandescent filament, and ballast lighting, which is fluorescent, HID, metal halide, mercury vapor, quartz halogen, and sodium lamp, as well as for resistive and general use loads. These contactors have a modular design that enables you to stock the building block components to assemble configurations of electrically held and mechanically held contactors, thereby reducing your inventory costs. Siemens Class CLM magnetically held and mechanically held lighting contactors are used in applications where it's critical that contacts remain in the closed position during a power outage. This means that the associated load will be automatically restarted when power resumes following an outage. This also means that the contactor only receives momentary current to open or close its contacts. Therefore, less energy is used and contactor hum is eliminated. A magnetically held contactor contains a permanent magnet. When the contactor is energized, current through a coil creates a magnetic field that reinforces the permanent magnet and closes the contacts. Current through the coil is then interrupted and the contacts are held closed by the permanent magnet, even if control power is lost. Contacts are opened magnetically when an off coil is energized. A mechanically held contactor has contacts that are mechanically held closed when the contactor is energized and remain held until a trip solenoid receives a signal to release the mechanical latch. Siemens Class CLM contactors are rated for tungsten lighting, incandescent filament, and ballast lighting, fluorescent, HID, metal halide, mercury vapor, quartz halogen, and sodium lamp, as well as for resistive and general use loads. As previously mentioned, Siemens offers enclosures for all sizes of contactors. They're designed to meet NEMA standards for most environments, including NEMA 1, 3R, 4, 4X, stainless steel, and 12. Siemens combination lighting contactors provide a disconnect means for lockout and maintenance, as well as short circuit protection. Furthermore, they're UL rated as service entrance equipment, permitting equipment to be pole mounted and installed directly off utility power lines. This makes the product ideal to control lighting in remote locations such as sports facilities, parks, fairgrounds, streets, and highways. It's also ideal for industrial and general area lighting. Numerous control options and accessories are available to customize the product to your exact specifications. To add flexibility, modifications are available as either factory installed or field kits. Nearly all these accessories are common for all lighting contactors, reducing inventory costs. Some of the common options include auxiliary contacts, solid-state control module, on-off push buttons, on-off and hand-off auto selector switches, pilot lights to display on-off conditions, control power transformers, control relays, 24-hour and 7-day time clocks. A pilot device directs the operation of another device or indicates the status of an operating machine or system. Siemens pilot devices and enclosed pilot devices are available with a variety of features and include product selections appropriate for a broad range of applications. The following pilot devices have a 30 mm mounting diameter, which refers to the size of the knockout hole required to mount a device. Class 50 standard duty and heavy duty control stations, Class 52 pilot devices, Class 52 Black Max corrosion resistant pilot devices. The following pages provide basic information for some of the types of devices listed above. However, before discussing these specific types of devices, we'll review some basic device concepts. A two-wire control circuit is so called because only two wires are used to connect the start-stop switch into the control circuit. This type of circuit provides low voltage release, but does not provide the low voltage protection. This means that when power is lost, the contactor will de-energize. However, as long as the start-stop switch is closed, the contactor will energize and the motor will restart when power resumes. Two-wire control is used for remote or inaccessible installations where it's desirable to have an immediate return to service when power is restored. A push button is a control device used to manually open and close a set of contacts. Push buttons may be illuminated or non-illuminated and are available in a variety of configurations and actuator colors. Push buttons are used in control circuits to perform various functions such as starting and stopping a motor. A typical push button uses an operating plunger, a return spring, and a set of contacts. The upper illustration shows a push button with one set of normally open contacts. Pressing the button causes the contacts to close. This push button has momentary contacts, which means that the contacts will open when the push button is released. Push buttons with normally closed contacts, such as the one shown in the lower illustration, are used in control circuits. The contacts remain in the closed position, allowing current to flow through them until the push button is pressed. Pressing the push button opens the contacts and interrupts current flow. The push button shown here also has momentary contacts. However, push buttons with normally open or normally closed maintained contacts are also available. Push buttons are available with various contact configurations. For example, a push button may have one set of normally open contacts and one set of normally closed contacts. This allows the push button to function as a normally open push button or a normally closed push button, depending upon which set of contacts are connected into the control circuit. The accompanying graphic shows an example of how a normally open and normally closed push button can be used in a control circuit. This circuit is an example of three-wire control because there are three connection points required to connect the start and stop push buttons and the holding circuit, MA. Three-wire control automatically provides low voltage protection, meaning that if power is lost, the motor will stop and will not automatically restart once power is regained. Pressing the start push button completes the path for current flow in the control circuit and energizes the M contactor coil. When the M coil energizes, the M and MA contacts close and power is applied to the motor. MA is an auxiliary contact that acts as a holding circuit by providing a path for current flow in the control circuit after the start push button has been released. When an overload occurs, the OL contacts open. The purpose of the normally closed OL contact in the control circuit is to de-energize the M contactor when an overload occurs so that the motor will not automatically restart after an overload. Selector switches are another means to manually open and close contacts and are commonly used to select one or two or more circuit possibilities. Selector switches may be maintained, spring return, or key operated and are available in 2-position, 3-position, or 4-position types. The basic difference between a push button and a selector switch is the operator mechanism. A selector switch operator mechanism is rotated to open and close contacts. Contact blocks used on Siemens push buttons are interchangeable with those used on compatible selector switches. In the accompanying graphic, a 2-position selector switch is wired to activate either of 2 pilot lights. When the switch is in position 1, PL1 is on, and when the switch is in position 2, PL2 is on. 2 common methods of indicating the contact position of a selector switch are to show an alternative position in dotted lines, or to use a truth table to show which set of contacts will be closed for each switch position. For the circuit shown here, the truth table indicates that contacts A will be closed with the switch in position 1, and contacts B will be closed with the switch in position 2. For a simple 2-position switch, a truth table has a limited value, but as the number of switch positions increases, the value of the truth table increases. A 3-position selector switch can be used to select any of the 3 closed contact positions. In the accompanying illustration, the selector switch positions, hand, off, and auto, are used to determine how contactor coil M for a pump motor can be energized. With the selector switch in the hand's position, contact position A, the M contactor energizes when the start push button is pressed. With the selector switch in the off position, contact position B, the M contactor coil cannot be energized. With the selector switch in the auto position, contact position C, the M contactor coil energizes when the liquid level sensed by float switch FS1 rises sufficiently to close the circuit. The M contactor de-energizes when the liquid level falls and the float switch contacts open. Indicator lights, often referred to as pilot lights, provide a visual indication of a circuit's operating condition. An indicator light may be wired to turn on for any predetermined condition. Indicator lights are available in a variety of lens colors to allow for quick visual indication of machine or process status. For example, Siemens indicator lights are typically available with a red, green, amber blue, white, or clear lens. The accompanying graphic provides a simple example of how indicator lights can be used in a control circuit. As shown in the diagram at the top, when contactor coil M is de-energized, normally closed auxiliary contacts MB are closed and the green indicator light is on to indicate that the motor is stopped. As shown in the middle diagram, when the start push button is pressed, contactor coil M energizes. The green indicator light turns off and the red indicator light turns on to indicate that power has been applied to the motor. As shown in the bottom diagram, the motor continues to run and the red indicator stays on after the start push button is released because normally open contacts MA are now closed. Control stations are used with magnetic controllers to control the starting, stopping, reversing, or speed of applicable motors. Siemens Class 50 control stations are assembled from up to 3 push button, selector switch, or pilot light units. Standard duty control stations are available in Type 1 surface mount or Type 1B flush plate mount. Heavy duty control stations have Type 4 watertight enclosures. Siemens Class 52 30mm oil-tight pilot devices and accessories are designed to provide long, trouble-free service in the most demanding applications. As the accompanying graphic shows, a wide range of devices are available. Also consider the following design features. Devices are smaller than earlier designs and require less mounting space. The modular design reduces the inventory needed to stock a variety of pilot devices. Illuminated device options include traditional incandescent lights along with energy-saving LEDs and extra bright cluster LEDs. Ribbed concentric lenses improve lighting distribution and aesthetic appeal. Devices are oil and dust tight and meet NEMA Type 1, 3, 3R, 4, 4X, 12, and 13 specifications. Class 52 30mm Black Max pilot devices are designed to withstand caustic and corrosive environments. They are made from heavy-duty, die-cast parts shielded with epoxy coating and meet NEMA 1, 3, 4, 4X, 12, and 13 specifications. Examples of harsh fluids these devices provide protection against include hydraulic fluid, heavy-duty lube oil, methyl ethyl ketone, and triloethylene. The voltage applied to the main terminals of an industrial motor is frequently higher than the voltage needed by the associated control circuit. In such cases, a control power transformer, CPT, is used to step down the voltage. In addition, the CPT isolates the control circuit from the power and lighting circuits, thus reducing electrical noise that could affect the operation of the control circuit. In the accompanying graphic, the voltage applied to the primary of the CPT is 460 VAC. This voltage is stepped down by the transformer to 24 VAC for use by the control circuit. Fuses on the primary and secondary sides of the CPT provide overcurrent protection. Other names for a control power transformer, the CPT, include control circuit transformer, control transformer, high inrush transformer, industrial control transformer, machine tool transformer. High inrush transformer is a name derived from one of the more important requirements of the CPT, the requirement to provide a relatively stable output voltage during conditions of high inrush current. When a control circuit energizes, as for example when a motor starter contactor coil is initially supplied current to too close to the contactor, the current required from its power source rises to as much as 10 times the current required to hold the contacts closed. This inrush current can last for up to 50 milliseconds, depending on circuit characteristics. As a result, if the power source is not designed to handle this inrush, the control voltage can drop below the level needed to energize the control circuit. A CPT is designed so that, if properly sized for the application, it will provide excellent voltage regulation in its secondary circuit, ensuring that the control circuit it powers receives adequate voltage. Selecting a control power transformer requires knowledge of the following concepts. Inrush VA. This is the transformer load voltage, V, multiplied by the current in amps, A, that's required during control circuit startup. Sealed VA. This is the transformer load voltage multiplied by the current in amps that is required after control circuit startup. Primary voltage. This is the voltage that will be supplied to the transformer primary winding. Secondary voltage. This is the voltage the transformer will supply to the control circuit. CPTs are chosen by selecting the transformer VA rating that will provide sufficient inrush VA, given the power factor for the circuit. Keep in mind that for any given transformer VA rating, a higher level of inrush VA results in a lower secondary voltage. Because NEMA standards require magnetic devices to operate successfully at 85% of rated voltage transformer ratings. Siemens class MT transformers are intended for domestic US applications and are available with maximum power ratings from 50 VA up to and including 5000 VA. Primary voltage is rated up to 600 volts, 50/60 Hz, and secondary voltage ratings range from 24 to 240 volts. These transformers are designed per NEMA ICS2 and are UL 506 listed and CSA certified. Siemens class MTG transformers are intended for domestic or international applications and are available with maximum power ratings from 50 VA up to and including 5000 VA. Primary voltage is rated up to 600 volts, 50/60 Hz, and secondary voltage ratings range from 24 to 220 volts. In addition to being UL 506 listed and CSA certified, these transformers meet IEC and EN requirements. Let's do our last knowledge check. Question 1. Siemens class blank lighting contactors can be converted from electrically held to mechanically held. Is it A, LE, B, LC, C, CLM, or D, none of the above? Question 2. A blank device directs the operation of another device or indicates the status of an operating machine or system. Is it A, contactor, B, control relay, C, pilot, or D, starter? Question 3. Contact blocks used on Siemens push buttons are interchangeable with those used on compatible selector switches. Is it A, true, or B, false? Question 4. Illuminated device options for Siemens Class 52 pilot devices include A, incandescent lights, B, energy-saving LEDs, C, extra bright cluster LEDs, or D, all of the above. Question 5. An important requirement of a control power transformer is to provide a relatively stable output voltage during conditions of high blank current. Is it A, inrush, B, nominal, C, steady state, or D, none of the above? It's now time for the final exam. Question 1. Contacts are shown in a control circuit diagram in the state that exists when the control device is A, de-energized, B, energized, C, normally closed, D, normally open. Question 2. Line diagrams are read from blank and blank. Is it A, left to right, top to bottom, B, left to right, bottom to top, C, right to left, top to bottom, or D, right to left, bottom to top? Question 3. Two types of circuits typically shown in line diagrams are the blank circuits. Is it A, control and electromagnetic, B, control and signaling, C, power and amateur, or D, power and control? Question 4. With an increase in current in the conductor, temperature will A, decline sharply, B, decrease, C, increase, or D, stay the same? Question 5. A/an blank occurs when too many devices are connected to a circuit or when electrical equipment is made to work beyond its rated capabilities. Is it A, arc fault, B, ground fault, C, an overload, or D, short circuit? Question 6. Which of these Siemens manual controlled products provides overload protection? Is it A, MMS manual switch, B, MRS manual switch, C, SMF manual starter, or D, all of the above? Question 7. An overload relay has A/an blank that identifies the maximum time in seconds that it takes for the overload relay to trip at a specified current. Is it A, ampere rating, B, continuous current rating, C, trip class, or D, voltage rating? Question 8. A motor starter combines blank. Is it A, a contactor and electromagnet, B, a contactor and an overload relay, C, an electromagnet and an armature, or D, an overload relay and instantaneous contacts? Question 9. One reason to use reduced voltage starting for a motor is to blank. A, apply torque gradually, B, increase starting torque, C, get the motor to full speed more quickly, or D, run the motor at low speed? Question 10. The synchronous speed of a three-phase induction motor is a function of the blank. Is it A, motor horsepower, B, motor full load torque, C, motor load, or D, number of motor poles and the supply frequency? Question 11. Which type of lighting contactor produces a humming sound during normal operation and is not recommended for a noise-sensitive area? Is it A, electrically held, B, magnetically held, C, mechanically held, or D, all of the above? Question 12. Siemens Class 14 ESP200 starters are available with contactor ratings up to and including NEMA size A, 4, B, 6, C, 8, or D, 10? Question 13. Which of the following settings for a Siemens ESP200 solid-state overload relay is made using a rotary dial on the front of the device? Is it A, full load amps, B, manual or automatic resets, C, trip class, or D, voltage rating? Question 14. A basic combination starter incorporates blank. Is it A, a disconnecting means, B, a motor starter, C, short circuit protection, or D, all of the above? Question 15. Another name for a solid-state reduced voltage starter is an blank starter. A, auto transformer, B, primary resistance, C, soft, or D, Y delta? Question 16. Which of these Siemens solid-state reduced voltage starters allows the phase control process to be applied in reverse when the motor is being stopped? Is it A, 3RW30, B, 3RW40, C, 3RW44, or D, both B and C? Question 17. Siemens class blank lighting contactors can be converted from electrically held to mechanically held. Is it A, LE, B, LC, C, CLM, or D, none of the above? Question 18. Illumination device options for Siemens Class 52 pilot devices include blank. A, traditional incandescent lights. B, energy-saving LEDs. C, extra bright cluster LEDs. Or D, all of the above? Question 19. An important requirement of a control power transformer is to provide a relatively stable output voltage during conditions of high blank current. Is it A, inrush, B, nominal, C, steady state, or D, none of the above? Question 20. Siemens Class 52 Black Max pilot devices blank are A, are designed to withstand caustic and corrosive environments. B, are made from a die-cast parts shielded with epoxy coating. C, meet NEMA 1, 3, 4, 4X, 12, and 13 specifications. Or D, all of the above? Well, that concludes the Siemens Basics of Controls for Construction. Thank you again for your time today. Take care.